All right, we're going to look at starting to do some inferential statistics in Chapter 10 that are on the difference of two parameters. And we're namely going to start with what are called the difference of two population proportions. So we're going to do intervals and tests and everything we've done on single means and proportions with two of them now. So what we want to think about is if we have two proportions, let's say P1 is the population proportion for males who do anything, who make over $100,000 per year. And let's say P2 is the population proportion for females who make the same. So what we're trying to do in a difference of two parameters is we're trying to see what is the difference between these two parameters. So if I subtract the two, if I do P1 minus P2 and I get 0, that means they're exactly the same. If I subtract P1 minus P2 and I get a number that's less than 0, then that means P1 was smaller. And if I do P1 minus P2 is greater than 0, then I know P2 is smaller. So what we're trying to do is we're trying to figure out what is the difference between these two parameters. Now, like always, a parameter is for all of the population, so it's a very hard thing to find. So we're going to estimate it using a sample statistic. Now, to estimate this, our sample statistic in this case is actually very interesting. Our sample statistic is actually the difference of two sample proportions. So we call those P hat 1 and P hat 2. So our difference is actually subtracting two sample proportions. So we call that P1 hat minus P2 hat. So what we're going to try to do is we're going to try to estimate the difference between P1 and P2 using P1 hat minus P2 hat. And that is going to be the goal of these problems. So just like we did before when we started with a single mean or a single proportion, we set up a sampling distribution. And the sampling distribution exists for the difference of two proportions as well. And we have it listed here. The shape of a sampling distribution of P hat 1 minus P hat 2 is normal if all the following are true. N1 times P1 in N1 times 1 minus P1, N2 times P2, N2 times 1 minus P2 are all greater than or equal to 10. So basically what we had before, except for we have to check it for every single proportion we have in every single sample size. So there's just 4 of them that all have to be bigger than 10 versus 2. The center of this distribution, the center of the sampling distribution for the difference of two proportions is simply P1 minus P2, which is in essence what we're looking for. And the standard deviation of the sampling distribution, or what we refer to a lot of times as the standard error, is this massive formula you see here. Square root of P1 times 1 minus P1 over N1 plus P2 over 1 minus P2 all over N2. So once you have this, just remember, if we want to ever find a confidence interval, we can use this standard error and our statistic to estimate that interval, because we remember that every interval is just the statistic plus or minus a critical value times the standard error. And since I'm telling you the standard error, and we know the statistic is P hat 1 minus P hat 2, we can make our confidence interval. So our confidence interval for the difference of two proportions is simply going to be given by this formula. So it has to be random, it has to be normal, meeting those conditions above, has to be independent. Then this is our formula. P hat 1 minus P hat 2. So there is our sample statistic, plus or minus Z star. And that's the same one from the table. You can use table B, which is the T table. The bottom line, remember that bottom line had, had the Z values, so you could just pick it out from there. And then we have that standard error formula, P hat 1 times 1 minus P hat 1 over N1 plus P hat 2 times 1 minus P hat 2 over N2. So the calculation is really just given by this formula. The trickiest thing really comes back to what we talked about. When you get these two numbers, what does it actually mean? Because remember, it's estimating the difference. It's basically estimating how far apart these two parameters are. So let's look at one example. There are students who study for final exams and some who do not. A study was investigating which group had a better success rate of getting an A on the exam. In the study, 50 students who did not study, and of those, 5 got an A. In a study of 60 students that did study, and those, 12 got an A. Compute and interpret the 90% confidence interval for the difference of two proportions. So what a good idea to do in this case first is to define what our two proportions are. So I am going to define the first proportion, P1, is the proportion of all students who got an A when they did not study. And then P2 is going to be similar. It'll be the proportion of all students, and again, it's all because we're talking about a population here. We're talking about everything who got an A when they did study. So our goal is to estimate what is the difference between these two parameters. Again, if it's 0, then that means that's what it is. If it is greater than 0, then the first one is bigger, and if it's less than 0, the first one is smaller, the second one is bigger. So let's go ahead and let's figure out what we have. Well, we know P hat 1, the information I got from P hat 1, I had 5 out of 50 who got an A when they didn't study. That's 10%. P hat 2, I had 12 out of the 60 who did study got an A. And that, of course, is going to work out to be 0.2. So we're going to use these two estimates to figure out what the difference between the two parameters are. So our formula, P hat 1 minus P hat 2, plus minus Z star, which we'll get from the table, big square root, P hat 1, 1 minus P hat 1, all over N1, plus P hat 2, 1 minus P hat 2, all over N2. So now we just have to put all our numbers in. Well, we know this first one's going to be 0.1 minus 0.2. We could have switched it, made it positive. It really does not matter. Plus minus. Now the Z star, this is a 90% interval. So if I go to my chart, look at the very bottom line of my T table, I get 1.645 times the square root, and then we just have to put these things in. So 0.1 times 0.9 over N1, there were 50, plus 0.2 times 0.8 all over N2, which is 60. And one thing I should mention, I should make sure all of these are over 10. Multiply the N times the P. I didn't do that, but I'll let you try that on your own just to verify they are. So now what I would have you do is pause the video, go ahead and figure this out, and we'll see if we can't get the same answer. So I'll go ahead and tell you that this one is going to be negative 0.10. Tell me what the margin of error is as you pause the video. Okay, so when I put all that stuff in, hopefully you get the same thing I got. I got 0.109940, etc., etc. So I'm just going to round it to 3 decimals. I'll go 0.110 would be the rounded value. So when I add and subtract that, if I take 0.110, or I take negative 0.10, and I subtract 0.11, I'm getting negative 0.21. So my lower bound is negative 0.21. And when I add it, my upper bound, I'm going to get 0.01. So let's talk about what we found. I mean, this is fine. These are great numbers, but it doesn't really talk about what it is. Now remember, this is estimating P1 minus P2. So in this case, in this number, since it's negative, we know P2 had to be bigger than P1. But on this number, it's slightly positive, but P1 is just a little bigger than P2. So really, it's saying that these two proportions, if I subtract them, the smallest they could be apart, the largest in magnitude they could be apart, is P2 could be 0.21 larger than P1, or P1 could be greater than P2 by 0.01. So the difference lies somewhere in there. So most likely that P2 is going to be bigger than P1 because it leans a lot more that way with the interval. But our conclusion would simply say we are 90% confident the difference between the two proportions and we probably should say the two proportions P1 minus P2, because if we switched it, it would be different, is between negative 0.21 and 0.01. So the negative is really just referring to the fact that the second one is bigger than the first one. And the positive is referring to that the second one is bigger than the first one. So if you were to ask a question, are these the same, or is one bigger than the other, you really couldn't answer it definitively, because on one end of the interval we say one is bigger, on the other end of the interval we say the other one is bigger. So it'd be kind of a hard thing to conclude. So the calculation's not terrible, but understanding and interpreting these is where it gets a little difficult. You can also do these on our TI graphing calculator, and I'll post another video that kind of talks about those functions and how you do it. And we'll kind of see if we can get the same answer that we got here.